Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, as promised before, this supposed to be a tutorial video regarding Faraday's law. Okay, before I continue solving problem, I would like to go back to the discussion regarding Faraday's law and how actually Faraday's law relate to Maxwell equations. So remember when we talk about Faraday's law based on experiment done by Faraday, he conclude that VEMF can be equal to minus the flux linkage over dt. Okay, and the negative sign in this equation is due to what is known as Lenz's law. Yeah? So that should be why the negative notation appear in Faraday's law equation. And if we talk about Maxwell equations, okay, for this particular equation, Maxwell state that curl of E is equal to negative dP over dt. Okay, and actually Maxwell equation is another form as what equated by Faraday in his equations. So the question now, how actually these two equations are interrelated. So that's what I'm going to explain, how actually Maxwell finalized this equation of Faraday. So because Maxwell actually a person that combining various equations such as Gauss law equations, MPS Circuit Law equation, Faraday law equation, and propose a chain of equations. So that's what Maxwell did, able to link all various independent equations to become one set of equations, which is very important in the world of electrical engineering. So that's what I'm trying to do in this discussion before I continue solving problem. So we like to show how actually this equation of Faraday been ended as what Maxwell equate here. Okay, so that's what we're going to do. Okay, to prove these equations, what we have to do, we have to rewrite this equation in more detail. So this equation, if we write in more detail, we can denote that VEMF is equal to negative N. N is the number of turns in our problem. The magnetic flux over dt. So remember the notation here is known as flux linkage. So flux linkage actually equal to number of turns multiplied with magnetic flux. So for the sake of discussion, so let's assume now, let's assume the number of turns equal to 1. Okay, therefore we're going to end with VEMF is equal to negative d magnetic flux over dt. Okay, that's what we're going to. So now, what happened then? So actually, when we talk about VEMF, as shown before in my previous video lecture, we can denote it to be equal of the closed loop integration of E dot dl. Okay. So I can rewrite VEMF is also can be written as the equation on the left-hand side. Yeah? So, and also I can expand the equation of right-hand side to become negative d over dt and then b dot ds. Because we have learned magnetic flux equal to the integration of magnetic flux density multiplied with the area. So that's what we are getting that. So now if we compare the most left hand side of this equation compared to the most right hand side of this equation, we can see they are slightly represented in different form of integration. For on the left is integrate respect to line, and on the right we integrate respect to surface. So what we have to do now, we need to adjust the equation so that both equations are represented in the same format of integration. What I mean by that, if the right hand side is integrate with respect to surface, so we like to convert the line integration to become surface integration. How we able to do it? So to do that, to convert from line integration to surface integration, we have to use what is known as Stokes' theorem. Okay. So I've talked about Stokes' theorem in my discussion of a curl of H equal to J. Remember that part of the discussion. So by using Stokes' theorem, what I can do now, I can have my equation now to be with respect to surface. Okay, what we are doing now, we are converting from line to surface. So Stokes' theorem said that we have to take the curl of E, YE, because we are referring to the E symbol here. Okay, since we are using the vector E, so you must also use vector E here. If we are using vector H as before, therefore it's curl of H. But since in this discussion, we are saying E, therefore it must be curl of E dot ds. Okay, so that's what Stokes' theorem does, converting a line integration to be in the form of surface integration by using this table or this set of notation. So for the most right hand side now, I'm going to readjust so that the integration appear surface. Then I'm going to have now minus dB over dt, and then I'm going to dot with ds. So now if we just focus on the notation in the red box, to this red box, by ignoring the front part of the equation as well as the back part of the equation, so we can say that whatever appear in this red box on the left equation is equal to the red box of the right equation. So this is what we tend to call it to be Maxwell equations. Okay, so that's what we have stated before. Maxwell equation is the other way of representing of Faraday's law. Okay, so this is what I'm proving to you in this introduction of tutorial video. Right? So this is what they are the same name, Maxwell equation of the form of Faraday's law. Yeah? So this is what you end with this set of equations. Okay, so now coming back to the intention of this video to do problem. So I'd like to refer to problem from our textbook, but since you can refer to, okay, we go back to the idea of Faraday's law. Yeah? Just want to make it a bit systematic. Okay, for Faraday's law, as what we have been shown, so there are three forms of EMF. First, we call it to be transformer EMF. And then second, we call it to be motional EMF. And the third type, we're going to call it to be the combination of transformer and motional, that we call it to be hybrid. Okay, so we have done example of transformer before. So we also have done a simple example of motional EMF in my previous lecture, but we have not do any example of hybrid EMF. But yet hybrid EMF is quite important in the world of Faraday's law because it optimizes the generation of EMF because it's used both conditions which are the magnetic field changing with time, as well as you are using the movement in the circuitry. So therefore you're going to have the most optimum design of EMF by utilizing hybrid. So for these examples, there's a lot in the textbook. So please refer to examples. I think you can 9.1 to 9.6. If you look at my textbook, they show a lot of example in detail. So therefore, I'm not going to do any example in my video because this example has been explained in very detail in the textbook. So page wise to be page 420 to 439, about 19 pages discussing about this example. So please help yourself with these particular examples, and I'm sure by going through the example yourself, because the example has been done in such detail, you can understand by reading through the solutions of the example. So what I'm going to do in my lecture, I'm just going to do the problem from the the back of the chapter. If you refer to our textbook again, page 473. Okay, this is the question. Okay, 473. Okay, so I'm going to do problem 9.6 here. Okay, so that's what we're going to do together, problem 9.6. I'm going to write again the problem slightly better so that you can see what we are doing. Okay, what we have now, okay, I'm going to give summary of problem 9.6 now. So what you have in this problem is you have the first conductor, infinite line conductor. Okay, so that should be the first information given by the problem. The first conductor is straight line and infinitely long. And the second information given, the current passing through, okay, is having a constant I, ampere. Okay, so and then to make it a bit easy to be solved, we're going to add coordinate. So the coordinate attached to this conductor is the z-axis. Okay, that should be the first information by the problem 9.6. You have a straight line conductor infinitely long, and the conductor carries current I ampere in the positive z directions. So what we can see from this particular problem, the current is constant. So what we can conclude here, constant current. Okay. So then what you given in this problem, another conductor, but now the structure is slightly different. The structure is a square loop. Okay, a square loop. A square, so then the dimension of this square loop conductor given as A. Okay, and then the distance here given as R. Okay, and then at T equal to 0, R equal to R naught. That should be known as initial condition. So this R equal to R naught at T equal to 0. So what happened then? this square loop conductor been shifted away from the infinitely long line conductor with velocity u naught in r directions. Okay, so now what you have now, a movement. Okay, so for sure now you can see logically they're going to be voltage of EMF induced in this conductor. Why? Because you have magnetic field in this region, then you are making the conductor move in this magnetic field, so therefore that condition will generate what is known as motional EMF. So therefore what the question wants us to do, okay, for t greater than 0, so meaning that when you are moving the conductor, prove that the VEMF induced in the conductor loop is equal to, let me see the equation correctly. So it's equal to mu naught A squared U naught I over 2 pi R plus A. Okay, so that should be the questions. Okay, so we're going to do this problem together. Okay, this problem taken from problem 9.6, page 473. Why I prefer to do this equation? Because this question already gave us solutions. So what we need to do, we need just to do using proper method of whatever EMF that we supposed to do, and then once we obtain the solution, if the solution agree with Sadiku, Alhamdulillah, our method is correct. If our solution not agreeable with Sadiku, meaning that something wrong with our method. I'm sure Sadiku is much better than us, so we cannot say Sadiku is wrong. Okay, so that's what why I choose this problem, because we have solutions already provided by Sadiku, so we just need to prove that our solution does agree with what Sadiku is proposing. Okay, so let's do it. So how we solve this problem? So to solve this problem, I think we have to look for the conditions. So since the B field is constant with time, and the circuit, okay, is moving, so meaning what circuit? The rectangular loop circuit is moving, so therefore we should adopt what is known as motional EMF. Agreed? Okay, to solve with motional EMF, we have how many set of equations that we can adopt? Yes, 2 set of equations. So let's list them. So the first equation that we can use is known as VEMF equal to, I think we have to do the integration first, B dot ds, and then we have to differentiate in order to get the solution. That should be our first set of equation that we can use. Or we can use the second set of equation that we proved together in our previous video, should be U cross B dot dl. Okay, so that should be the logical step regarding motional EMF. Which set of equation that we should use? The first one or the second one? So you can use which one you prefer. So I'm going to choose mine because I can see information given in the question involving velocity. So, and then I can see in equation number 2, this information of velocity. So I think I'd like to adopt equation number 2 in my solutions. So therefore, I'm going to sit now. I'm going to use equation 2. Okay. So now, when I look into the problem, I can see the structure is not only straight line. It consists of a bit complex. It's meaning a rectangular structure. So from our experience solving problem before, which is also a rectangular structure, but the only difference in that scenario, the structure move in a rotational manner, whereby in our structure here, involving linear velocity. So therefore, from those experience, what we have to do, I'm going to split the problem into simpler structure. I'm going to state to myself, I'm going to label this side of the loop to be side number 1. Okay, this side to be side number 2, and this to be number 3, and finally I'm going to label this to be number 4. And from the above structure, we can state that, okay, from above structure, we can state that the VMF that we're going to calculate in this problem is equal to what? Yes, we're going to isolate each structure of having its own induced EMF. You see, I'm repeating the problem as what we have done before, but the only difference, the detail complexity of the problem is slightly different. Before is angular movement, but now is a linear movement. But yet the idea of basic method is still the same. So therefore, I'm going to solve the problem individually. So I mean by that, so let's do for VMF number 1. Yeah? VEMF number 1. Okay, so let's draw it. So now my problem involves the source of field. Okay, this should be our source of magnetic field. And then we're going to have the moving conductor. Okay, distance wise to be R. The width, the length to be A. And then this conductor is moving with U naught in R directions. Okay, so how we continue solving this problem? Yes, we're going to take sample. I'm going to take sample here. So my sample going to generate its own EMF. So I'm going to call now that sample going to produce its own induced EMF number 1. And we're going to refer to our equation number 2 of saying that U cross B dot DL. Okay. So we have to now relate the equations to our diagram. So what's U? Well, U in this case is known as U naught R, given by the question, and B. Okay, how do I determine the B? So the B must be the B appearing in this region due to which current source? Yes, due to this current source. Then how do I able to find the B from the current? Good. You can use either Biot-Savart law or MPS Circuit Law. But since our straight line conductor is infinitely large, therefore the logical method that I can use to find B from I will be MPS Circuit Law. Okay, so I'm going to say that using MPS Circuit Law. Okay, remember you have to use MPS Circuit Law. What is MPS Circuit Law states? H dot dl equal to I enclosed. Okay, and then by using proper method, we're going to find H equal to I over 2 pi r in the phi directions. And assuming the medium here is free space, therefore the B will be equal to mu naught I over 2 pi r in phi directions. Okay, so that should be the steps. So you can see now, even though in the world of electromagnetic world, but yet we have to use the concept that we learn in the world of static to be specific here, magnetostatic, which is MPS Circuit Law. So therefore, what we're going to set now, U cross B will be equal to U naught mu naught I over 2 pi r. So in which direction? So now r cross phi will give us z directions. Based on which coordinate system? Cylindrical coordinate system that we have seen in week number 1 of this subject. So r cross with phi will give us z direction. So that's, alhamdulillah, we have completed this part. Now, I'm going to continue now finding my DL. So what should be the DL here? Okay, so if we refer to the coordinate system that we denote earlier, this is given as z-axis. Due to that parallelity, where you can see now the DL shown here is parallel to this axis, I'm going to state now my DL is given a standard symbol in cylindrical to be dz in z directions. Okay, so having that been extracted from our diagram, so let's finalize our VEMF number 1 here. Okay, finally we're going to state now VEMF 1 will be equal to the integrations of U naught mu naught I over 2 pi r in z directions dot with dz in z directions. So therefore I have to choose limit now. So looking at our problem here, the length of this conductor can be related to from 0 to A. So I'm going to put from 0 to A. And you can see the way I'm choosing the limit is very critical here. So why, I'm going to explain later on. But at this point, at this junction, you must observe I'm choosing the limit of this integration from 0 to A. For those who want to choose the limit of integration from A to 0, it's nothing wrong with your method. Okay, but yet you have to link that selection of limit integration with your solution later on. So what I'm going to have by doing this integration is going to end with, what is it? Yes, mu naught A U naught I over 2 pi r. So that should be our VEMF number 1. Okay. So now what we should do then, we're going to go back to our initial plan we have done for this particular part of our intentions. We're going to continue with the second part now, finding VMF number 2. Okay, so VEMF number 2 now. VEMF number 2. So let's redraw the problem again. So what we have here, straight conductor, infinitely long, carrying current I, located along the z-axis. The second conductor is this conductor, side number 2, and then moving in these directions U, not R direction. So what we have, still a conductor moving in a medium containing magnetic field generated by the current in this straight line conductor. So now we can find the VMF here. Okay, so this VMF we're going to label as D VEMF number 2. And mathematically, it must still the same as before. U cross B dot D. Okay, let's label this distance to be R. Okay, the distance here to be R. Okay, so therefore, what we're going to have, the B still as before. Okay, so therefore, our U cross B will be equal to what we have obtained before, mu naught okay, U naught I over 2 pi R in Z directions, correct? That should be the one that we should have, is exactly as before. Yeah? Mu naught, U naught I over 2 pi in Z directions. Okay, but yet when we look for the DL here, okay, the DL here now, so the DL must based on what we, the position we are taking the sample on the conductor. So this is our DL. So based on this particular sample position, the DL cannot be dz anymore because it's constant with respect to z, but it still varies with respect to r. Therefore, the DL should be replaced with dr in r direction based on cylindrical coordinate. Okay, so if I do the mathematics of z dot r, what going to be my solution? Yes, it's going to be 0. Okay, due to that argument, the dot product of z dot with r will give us 0. So the 0 comes from the dot product reasoning. So now what we can conclude, VEMF number 2 going to be equal to 0. Okay, so I'm going to do the VMF number 3 now. Okay, so let's look at the diagram. Then we're going to use our previous solution as our guidance. So we're going to have infinite current source. Okay, you're going to have another conductor, side number 3. But the distance here is no more R, but it's becoming R plus A. Okay, and then this particular side number 3 still the same, moving in the same directions, U here. Okay, so by seeing that and comparing with our previous solutions, what we can say that VEMF number 3, if you do it properly, is going to be not equal to 0, because that's what I have proven in side number 1 is produced VMF. So it's going to be mu naught A U naught I over 2 pi, yes, R plus A. That should be the only difference, the distance. Okay, therefore what we're going to see, the induced EMF in site number 3 having less magnitude compared to the induced EMF in site number 1. And for VMF number 4, if you care to do it, it's going to be the same as VMF number 2. Should be equal to 0. So now, what I have to do, I'm going to represent the solution in a graphical form. Remember, the way we take the integration limit from 0 to A. Okay, so therefore, what I'm going to say, since I'm taking the integration from 0 to A, therefore, for site number 1, I'm going to draw my source to be such manner. Why? Because I'm doing the integration from 0 to A. Then I obtain this to be positive VEMF number 1. Similarly, I'm also doing my integration of leg number 3 from 0 to what? Yes, to A. Therefore, going to have this, and then the solution that we obtain here also positive. So therefore, it's going to be my VEMF number 3. So therefore, 0 for site number 4, 0 for site number 2. So that should be our equivalent circuit of induced EMF in individual part of the structure. So to find the final solution, I'm going to use what you have learned in circuit theory. That should be my final solution. So my VEMF, which is the resultant VMF, should be equal to what based on circuit theory? Yes, VEMF of 1 minus VEMF of 3. Okay, because we are utilizing circuit theory now to find the resultant induced EMF in the rectangular loop. Because the polarity positive for both sides, so to find the resultant should be this one minus this one, and then that's what you have this. So let's substitute. So this should be equal to mu naught A U naught I over 2 pi R minus mu naught A U naught I over 2 pi R plus A. Okay, so that should be, and then if we going to simplify the solution, we're going to take the common term, okay, over 2 pi. So this one should be 1 over R minus 1 over R plus A. Okay, so you can have R plus A here, R here, so therefore you're going to have the final solution equal to mu naught A squared U naught I over 2 pi R R plus A volt. Okay, which is exactly the same as what Sadiku asked us to prove in that particular problem. So there you are. So what I'd like to address here, the notation of your induced EMF will be depend on the limit of integration you are taking in the problem. So the way I'm taking the limit of integration from 0 to A, and I'm having the solution to be positive, I draw the battery orientation to be as such. Since I'm also taking the limit to be the same from 0 to A, and it's also producing the same positive sense, I'm going to draw it as such. So therefore, the way you able to link the limit of integration to the way you're going to represent the polarity of your induced EMF is very crucial in this particular approach. So therefore, it's very important for you to know that the way you are doing the limit of integration. You don't have to memorize formula. You can just deduce based on the way you execute your mathematical solutions. Okay, so I think it's enough for me to talk about EMF, or in more general Faraday's law. Again, I'd like to stress that you must go and do your self-examples regarding hybrid EMF, because there's a lot in the textbook. I'm not going to repeat it. Hopefully, by going through the detailed explanation, you're going to understand about it much clearer. So, Alhamdulillah, thank you for your attention and participation. Inshallah, we're going to see each other again in my coming video. Assalamu alaikum wa rahmatullahi wa barakatuh.